Questions about anything from last time or anything? Today I'm going to do some famous applications of some of the tools we've been developing. Last time near the end I was talking about using Lebesgue's integrability criterion to demonstrate something kind of subtle about Riemann integrable functions. So this famous criterion is that f is Riemann integrable if and only if it's bounded and continuous almost everywhere. I guess I'll say one last time what this almost everywhere means. It means a set AB, the interval is AB, and almost everywhere means it's continuous at every point in AB minus a set S of measure 0, where S is of measure 0. And that's the funny thing about Lebesgue integral. It's hard to tell. It's hard to explain what the measure of the general measure of a set is, but measure 0 has a very simple meaning. And measure 0 means given epsilon bigger than 0, I can cover S by a union of open intervals A and Bn, where the sum of the lengths of those intervals, so the lengths of those intervals would be Bn minus An. They're individually small, but they add up to be smaller than epsilon. So not only individually small, but that when you sum them, you get something that's still small. Okay, so that's the meaning of that mouthful. Questions about that? Well, last time I used this fact to show that if f is Riemann integrable, then the absolute value of f is 2. And that was an easy application of this Lebesgue's criterion, because if f is continuous almost everywhere, well, where f is continuous, the absolute value of f is also continuous. That was an exercise a long time ago. And therefore, the absolute value of f would satisfy the Cauchy criterion. Not Cauchy, Lebesgue's criterion. So the proof is easy when you use the Lebesgue's criterion. Proof. I did it last time. Check. And in fact, so it's worth mentioning that there's a little thing called the composition theorem that's using the same idea. Let's suppose that f is Riemann integrable. Okay, we'll suppose that, and we'll suppose that f maps the interval AB into some interval CD. F is bounded, since it's Riemann integrable, and we're assuming it just maps there into an interval CD. Well, the composition theorem says if phi is continuous, on CD, then phi composed with f is Riemann integrable. And the proof is basically what I did for the absolute value thing. So the proof is easy when you assume that Lebesgue because if f is continuous almost everywhere, then phi composed with f would be continuous almost everywhere. So phi composed with f is continuous where f is. And so being continuous almost everywhere would carry through for phi composed with f. And of course, phi composed with f would also be bounded, because continuous functions on a closed interval, assume they're max, they're bounded. Questions about that? Well, the fun thing to think about using this fact, here's an interesting thing. If f and g are continuous, then f times g is. And we know that continuous functions on a closed interval are Riemann integrable. We showed that by uniform continuity. So fg continuous implies fg is Riemann integrable. And then here's the question: does f and g both Riemann integrable imply that their product is? F, g both Riemann integrable imply the product is. And the answer is yes when you use the composition theorem. Yes. You don't see it, I mean, it's not immediate. In fact, without Lebesgue's criterion, you'd have to do some major thinking to demonstrate this. But the answer is yes. And let's see, why is that? And that's because the square function is a continuous function. X goes to x squared is a continuous function on any interval. Continuous on any interval CD. So if f and the composition theorem then shows that, yields I should say, that f g Riemann integrable would yield that f squared and g squared are Riemann integrable. How can I get that fg is Riemann integrable from that? It's a fun trick. So you sit around for a little while and think, what the heck do I do next? Well, f and g in Riemann integrable would imply that f plus or minus g, let's do plus g is Riemann integrable too. So f plus g squared is Riemann integrable. And now the aha moment is when I write this out, I would get f squared plus 2fg plus g squared. F squared is in there, g squared is in there, and so fg is in there. So the aha, fg is Riemann integral. That's kind of a tricky little thing. Questions about that? Well, now that we've got sort of the basics of integration, actually, these facts I'm telling you are more philosophical, of philosophical interest. And when you start thinking about limitations of the Riemann integral, you're led to all kinds of subtle things about real functions. In fact, quite subtle. And so whenever engineers and scientists are doing integration, they usually have, continuous functions or piecewise continuous functions or something sort of explicit and not pathological. Nothing like the Thomé function, which is pretty weird. I suppose in quantum mechanics you might run into some pretty wild and crazy things, but classical science and engineering would call this a philosophical question rather than an important one. Well, it's important for math because a lot of math was discovered and developed to study these issues. Anyway, some of the basic tools to really use integration in a meaningful way. A big one is the technique called integration by parts. Which you learn in freshman calculus. And of course the book likes to streamline notation. And so the thing you learned in freshman calculus was integral of u dv equals uv minus the integral of v du. And that's the indefinite integral version of it, or the integral from a to b of u dv equals uv evaluated between a and b minus the integral from a to b of v du. Okay, and that's how you remember the thing. That's how I remember it, the formula. And let's see, what do these things stand for? This would stand for the integral from a to b of u of x. dv is shorthand for dv dx dx. And this would be u of x, v of x evaluated between a and b minus the integral from a to b of v of x. And du is shorthand for du dx. dx. Okay. And so let's see, what does the book do? Let's see. V is an antiderivative for dv dx. So the book would call this v an f. And if dv dx is an f, then little v would be an antiderivative for little v would be an antiderivative for dv dx. Okay. And let's see, then the book would call du dx little g. Let's see, I have an F here. This V is also a capital F. Okay, if little g is du dx, then u would be an antiderivative for little g. And the book would call that capital G. And so U is a capital G. And so the book writes this famous formula as integral from A to B of f times capital G, and it skips dx, which I find irritating, equals the antiderivatives of these two things from A to B minus the integral from A to B of capital F little g. It's the same thing you learned in freshman calculus. Except I can't remember it that way. But the proof, and as the proof is the same as also for freshman calculus. I'll do the proof using u's and v's. So u v prime is, by the product rule we learned, u v prime plus u prime v. And then if you combine with that with the fundamental theorem of calculus, integral from A to B of u v prime dx, that would be equal to integral u v prime dx from A to B plus the integral from A to B of v u prime dx, which is shorthand for dv. And this one is shorthand for du. I mean, du is shorthand for that, u prime dx. And then on this side, you just use the fundamental theorem of calculus that we learned in this section, even though we already knew it. So that would be uv evaluated between A and B. So the freshman calculus, I mean, it's just the product rule and the fundamental theorem combined. You might remember that I started the first lecture of the course with Fourier series. I plan to have the last lecture in the course be the thing I promised, namely that we can understand that Fourier series converge using these tools. And so I thought here's a fun fact we can do from using integration by parts. Fun fact. The Fourier coefficients tend to 0 as n goes to infinity when the function we're studying is C1 smooth, meaning f and its first derivative are continuous. F is continuous. F prime exists and is also continuous. I guess if f prime exists, we know that f is continuous. And is also continuous. That's what C1 smooth means. And the proof is just integration by parts. So let's see. The Fourier series for f is, I'm putting here corresponds rather than equals. The big question is this an equals? And it is in this case. So that it's a naught plus summation an cosine nx plus bn sine nx as n goes from 1 to infinity. And the interval we're talking about here is on minus pi to pi. And A naught is 1 over 2 pi, the average value of f, the ANs are 1 over pi, integral from minus pi to pi, f of x cosine nx. And the reason these can be, Johann Bernoulli was able to figure out what these coefficients needed to be, was the orthogonality property of the Fourier functions. And the Bn is a similar thing, but with sine in place of cosine. Okay, so let me show you why this, so the proof that the Fourier coefficients go to 0 is easy. Proof that an and bn go to 0 as n goes to infinity when f is C1 smooth, so C1 and AB. Not AB, minus pi pi. And it's just integration by parts. I'll just do one of them. Let's see. I'll do the ANs. AN is one. I guess I should copy and paste. Is this f of x cosine nx dx. Well, this is the d. This is dv. And f is going to be the u. And let's see if if f is u, then f prime of x would be du. F prime of x dx would be equal to du, shorthand. And if dv is cosine nx, then v would be the integral, antiderivative of cosine nx dx, and that's equal to 1 over n, and the 1 over n is the key. That's exciting because that's going to go to 0. Okay, so it's 1 over n sine nx. And so when I do the integration by parts, I would get u times v. Let's see, u is f of x. V is 1 over n sine nx. And we evaluate that between minus pi and pi. Sine n pi's are 0. So what luck? That's 0, independent of what f might be, because sine n pi is 0. And then here we would get minus integral of v du. And so that would be the integral from minus pi to pi. V is 1 over n sine nx times du, which is f prime of x dx. And so now I can write an is less than or equal to that integral. And I can pull the n 1 over n in front, and then I would get the integral from minus pi to pi of, I can put the absolute value inside. That's one of our inequalities I deduced last time. Sine nx times f prime of x dx. And so then I would get less than or equal to m over n, where, let's see, what would the m be? Let's see, m would be equal to the max, let's see, the max of sine. the sine of n of x is always less than or equal to 1. Even though it's wiggling like crazy, it's bounded by 1. And so m, if I estimate this, the maximum m is going to be the max of f prime on minus pi to pi times the length of that interval, which is 2 pi. That's the length of minus pi to pi. And sure enough, that goes to 0. And the b is similar. Questions about that? That's an important fact. That's called the Riemann-Lebesgue lemma. Just knowing that Fourier coefficients go to 0. Riemann figured he would have known this because this is kind of easy and straightforward. Riemann proved that if something's Riemann integrable, then the coefficients still go to 0. So this is a famous theorem, famous fact. Called the Riemann-Lebesgue lemma. Let's see, Riemann showed that if f is Riemann integrable, then the a-n's and b-n's go to 0. And Lebesgue showed that if f is Lebesgue integrable, f Lebesgue integrable, same. So Riemann integrable functions are Lebesgue integrable, but you can find Lebesgue integrable functions that aren't Riemann integrable. In fact, the one that's 1 on irrational and 0 on rational is the classic, easiest example. Okay. Well, let's see, the big theorem in this section, which is also just integration by parts, is Taylor's theorem with remainder in integral form. And the integral form is sometimes needed, where the mean value theorem kind of form is not as useful. So with remainder in integral form. And I would say this proof is rather straightforward when you get down to it. Let's see what it is. What is it? We're going to suppose that let's suppose I want to assume that all these derivatives exist, f prime, f double prime, out to the n plus first derivative exist on some interval. And that the nth derivative is Riemann integrable. So because those derivatives exist, the f all the way up to the nth derivative would be continuous. A remark, you might as well feel free to assume fn plus 1 is continuous. I don't want to get bogged down in the little tiny detail that would improve it. Because whenever you're applying this theorem, you're doing it to sines and cosines and exponentials and functions that are infinitely differentiable, usually. So, it's a fact that you don't have to assume this, but I'm going to assume it just to make it easier. Then the conclusion is we can express f of x in terms of a Taylor series. So let's see, f of a plus f prime of a over 1 factorial, x minus a plus etc. out to the nth derivative at a divided by n factorial times x minus a to the n plus a remainder, Rn of x. And now instead of a point C that's between x and a, we get a very explicit way of writing this remainder, where Rn of x is equal to 1 over n factorial integral from a to x n plus first derivative of t. T is a variable of integration. X minus t to the n dt. Okay. It looks like this is going to be a bear to demonstrate, but it's not terribly hard at all. So let's see what's the proof. The proof is integration by parts. Integrate Rn by parts. That's all there is to it. And you'll see you can do it again and again. So let's see. I'm going to write I'm going to copy this thing. I'm not going to copy it. I'm going to rewrite it. Let's see. Rn of x equals 1 over n factorial integral from a to b. All I'm going to do is change places. Yeah, thank you. Okay, that's all I'm going to do. And when I do that, then I realize, aha, I'm going to use integration by parts. This should be my dv. And this should be my u. Then, of course, du would be n times x minus t to the n minus 1 times minus 1 dt. Because of the minus 1 inside that. That's the chain rule. Okay. And if dv is that, then v would be the nth derivative at t. Anyway, you do it once. I'm not going to do the gory details because it's just a matter of writing it down and enduring. So when I do it once and take the limits, I would get the nth derivative at a times over n factorial times x minus a to the n. And then, let's see, when I multiply that n factorial by n, that turns it into an n minus 1 factorial. And then what's left is an integral from a to x of the nth derivative at t. And now here I would have x minus t. X is like a constant in these calculations, to 1 degree less. And now you realize, oh my gosh, I have the same stupid integral, but with the n is 1 less. And so now it's just a matter of repeating it. So repeat. And then you get, let's see, when you do it, you get minus, this one would stay the same. And then the next one would give you a minus, the one that's lower by 1. Minus dot, dot, dot. And the very last one would spit out a minus f of a. Then you stop. So I repeat. And the last one right here is when you stop. And when you look at that equal to the original Rn, that's the result. So it's not terribly difficult. It's just a matter of having the patience to sit down and do it and realize the last one is f of a times x minus a to the 0th power. Questions? Let's see. Well, I thought of a fun application of this stuff we've been doing would be to analyze the trapezoid rule. So here's a fun thing. Remember in freshman calculus you learned the trapezoid rule. So you had a function. There was a rectangle method and there was a trapezoid rule. So the rectangle method, so maybe you use the left endpoints. See, we have an a here. And then we would partition this into delta x's. Oh, blast. B. And then the trapezoid rule calls for you to find the areas of these trapezoids. Oh, I should have made them bigger so they look like trapezoids. And you can write a formula for adding up the area of these trapezoids. And so you're approximating the area under the curve by adding up these areas of the trapezoids. And the question is, how small do you have to make your delta x to approximate that area within some tolerance? So this is the famous trapezoid rule. And this is in section 7.5. Would write out the formula that you learned in freshman calculus. So the question for an engineer, if they really want to use this thing, is how do you know when you're close enough? So you get, how to know when you get the integral from a to b of an f dx within some tolerance. Okay, and this is a typical application of the tools we've been studying. Turns out not to be hard. Let's assume that f is as differentiable as we want. So let's assume, in fact, let's assume that f is C2 smooth on AB, which means the first and second derivatives exist and are continuous. So f prime, f double prime exist and are continuous. Okay. You'll see why I need that in a second. Then I'm just going to draw one little piece of it. Let's have, I'll make my function bulge enough so you can see. Here's my partition. Here's an xn minus 1, and here's an xn. And here's that secant. And then the area I'm calculating is that orange stuff. And this little, I'll make a little red line here. That's really small. The error, when I calculate the trapezoid method compared to the actual integral, the error is that area of that little crescent. And let's see, what would that be? Let's say I should take the absolute value of the error. And the error is going to be the integral from xn minus 1 to xn of f of t. That's the thing on the top, so this is the t direction. Minus, let me graph that green line. The graph of that green line, we've kind of seen it before in the mean value theorem. It's x of n minus 1 plus f prime of xn minus 1. Oh, let's see. Oh, crud. The slope of that thing is the average. Let's see, it's f prime of xn minus 1 plus f prime of xn over 2 times t minus xn minus 1 dt. And I want to estimate that error. Okay, so what I see something here. This looks like something straight out of the mean value theorem. This would be an f prime of c. I'll call it a cn. Where cn would be between t and xn minus 1. And so this would be t minus xn minus 1 in the mean value theorem. I am missing a parentheses right there. Okay. Now I'm going to continue to mess around with that stuff there. If I put all those under one thing, I would get 2 times f prime of cn. And here I'd get, I'm going to put this over 2. I get 2 times that derivative. I can pull the t minus x minus n minus 1 out here. And then I would have here minus an f prime of xn minus 1 minus an f prime of xn. And now I realize, aha, I can pull that apart and get f prime of Cn minus f prime of xn minus 1 plus f of the other one. I have 2 there, so I'll put 1 over here. And I'm going to use the mean value theorem again. Let's see, this is all over 2. So the brilliant idea is to use the mean value theorem again. And let's see, then I would get, I'm estimating the absolute value of this thing. And so I would get an f double prime of something. I'll call it a Cn prime, because it'll be a different Cn. That Cn is going to be between Cn and xn minus 1. This one is going to be between Cn and, let's see, so this one is going to be Cn minus xn minus 1. And this one's going to be f double prime of another Cn, call it double prime. And this one is xn minus Cn. Okay, so let's let m be the max. The max of f double prime on AB. Then this would be less than or equal to my max times, and this Cn minus xn minus 1 is less than my delta x. And the other one would also be less than the max, and that thing is less than delta x. Okay, and looks like my delta x is b minus a over some big number n. And so I got that little one trapezoid error. The error is less than or equal to, let's see, the thing inside the integral, it's less than or equal to integral from xn minus 1 to xn, and here I got m over 2, no, I got 2m over 2 is m. So here I got m times b minus a over n dt. And that's an interval of length. So this is going to be less than or equal to m times b minus a over n. Oops. I got to go back and look at my thing. Ah. I haven't used this thing yet. This one is going to give me another, that thing is also less than delta x. And so I get another delta x when I estimate it. T minus x, right. This one right here. I haven't been messing around with that one. So I'm going to get another delta x. I've estimated this thing in the middle, and I have to get another one here, the green one. That's b minus a.